Hi, thank you for coming to see my presentation. My name is Chaeyong Park and I'm a graduate student at Post-Tech South Korea. I'm going to talk about our paper, Vibration-Augmented Buttons, Information Transmission Capacity, and Application to Interaction Design. Either physical and virtual buttons are vital components in the most input interfaces. However, those button input interfaces have both advantages and disadvantages. To this end, vibration-augmented physical buttons have emerged as a new alternative offering advantage of both physical and virtual buttons. This simple technology affords a variety of feels to a single physical button with providing additional vibration. Ogawa first presented the idea with a compact prototype. Shim applied the idea to a gamepad for demonstration. And finally, Park expanded the idea by designing many augmented buttons and quantifying their perceptual effects. Inspired the previous study, we proceed to finding effective design method for vibration-augmented buttons. Firstly, we investigate human channel capacity of vibration-augmented buttons by adopting the information theoretic framework. Then, we applied the findings to designing an effective text entry method for virtual reality. Before introducing my research, I explain information transfer. Humans have a limited ability to identify different sensory stimuli. Here, the information transfer means the amount of information obtained by communication. Furthermore, information transmission capacity determines the recognition ability of human systems. Our design and selection of vibration-augmented buttons were inspired by the previous study of Pearl. We replicated their hardware and designed 20 augmented buttons by varying vibration frequency and energy. Also, we used the tactile sensation of buttons, which were distributed in a 2D affective space. Here, the affective space provides valuable information for composing a set of augmented buttons. For example, selecting augmented buttons far from each other in a space can improve the set's information transmission capacity. In addition, abstract meanings of button field can facilitate the user's recall. In the first experiment, we estimated the information transmission capacity of augmented buttons by conducting an absolute identification experiment. We selected the augmented button sets from the 4 quadrants in the affective space, while balancing both their perceptual qualities and physical properties. In the experiment, participants were asked to choose the correct button among the provided and augmented buttons. To analyze the result data, we computed 2 matrices, the percent correct score and information transfer. The confusion matrices for the 4 sets are shown in this figure. The bar graph shows the PC and IT scores, and the IT score was maximized to 2.6 bits. Equivalently, the participants near perfectly recognized 5 to 6 buttons when more than 8 augmented buttons were presented. Also, the highest IT score of our augmented buttons is comparable to the results of other research for estimating IT values of vibratactile stimuli. After studying the information transmission capacity of augmented buttons, we carried out another experiment to measure the IT of commercial physical buttons. We selected 8 physical buttons. They have different operating structures versus click field and indentation depths. The result shows that PC score is 74.7% and the IT score is 2.32 bits. It means about 5 button click sensations could be near perfectly identified with no errors. The IT of the physical buttons was slightly lower than the IT of vibration-augmented buttons. Thus, this comparison advocates that Augmented buttons provide distinctive perceptual and affective experience to users. To showcase the anticipated benefit of identifiable augmented buttons, we designed and implemented an application for typing text using a handheld controller in a virtual environment. We made a mock-up VR controller containing an augmented button. Normally, the controller's physical button provides the same haptic feedback regardless of the system state. However, our augmented button enables event-driven variable haptic feedback. In this application, our system provides different confirmation feedback for 6 different types of input errors. Users perceived a soft and blunt button feel when typing the correct character, and they obtained different button feels depending on types of input error. Finally, we conducted a user study that evaluated the benefits of our VR text entry application. Participants were presented with 2 different conditions during the text entry: single pattern, which always present the same button feel regardless of their state, and multiple patterns, with the selected 6 augmented buttons. Their task was to type a phrase displayed on the screen as quickly and accurately as possible. To evaluate task performance, we measured text input speed and accuracy by calculating the word per minute and the text error rate. Also, after typing all phrases, participants answered the cognitive workload and haptic experience. The results show that variable button fields improve the task performance. Also, our system reduces cognitive workload and improves the haptic experience of text entry in VR. The reason seems that participants will recognize the haptic error message of multiple patterns and corrected errors instead of making successive errors. The contributions of this work are detailed analysis of the information transmission capacity of vibration-augmented buttons and a successful demonstration of the interactive application using augmented buttons. This is end of my talk. Thanks for watching it.